Here for the second chapter, our Introduction to Python and Programming. And this session is going to be all about fundamental data types. So we're going to be covering variables as well as arithmetic or arithmetic, depending on how you want to say it. And maybe we should look at this plain billboard, I guess, on the right-hand side, and consider some of the information that's being stored here. We have flight numbers, which are whole valued numbers. We also have destinations, which are strings of characters. And then finally, we've got gate numbers, which are a combination of a letter as well as a number. Okay, and these are going to be important data types in any Python program that we use. And in the chapter, we're going to learn about how to work with these numbers and the text, and how to write simple programs that perform useful tasks with them. So this leads to our first kind of main topic for this session, being variables. Most computer programs are going to hold temporary values in named stored locations. Programmers name them so that they can easily access the information stored within them. There are many different types of storage to hold many different types of things. You define a variable by telling the compiler what name you will refer to it, as well as the initial value being stored in it. So I like to think about variables as buckets. I have a name on the front of the bucket, and inside the bucket is some value. I refer to the value stored inside the bucket by the name of the bucket. Other people like to think about a kind of multi-story car park or a car park garage sort of thing, where you have a bunch of car parking spaces. They have a reference of some sort to refer to the specific car parking space, and inside the car parking spaces is some value, typically a car. So we're going to be looking at variables. So how do we define a variable? To define a variable, we need to specify an initial value. We use the assignment statement, which is a single equal sign, to place a new value into a variable. So our examples here are a equals 6, amount equals 60, and number of students equals 150. So for a equals 6, we have a bucket with the name A on the front, and inside the bucket is the value 6. We have another bucket with the name amount on the front of it, and inside that bucket we have the value 60. And then finally, we have a third bucket with the name number of students on the front of it, and inside that bucket we have the value 150. And again, you could think of this maybe like a multi-story car park, where you have a space in your multi-story car park whose name is A, and inside that space we have the value 6. You have another space whose name, or how you'd refer to that space, is amount, and inside that space we've stored the value 60. And we have another car parking space in our multi-story car park called number of students, and inside that car parking space we have the value 150. It's important to note here that a single equal sign is not being used for comparison. A single equal sign is being used for assignment. It copies the value on the right-hand side of the equal sign into the variable, which is on the left-hand side. We're going to learn more about the comparison operator in the next chapter. The comparison operator is a double equals sign. Okay, so the value on the right of the equal sign is assigned to the variable on the left. So we have a variable called total, and we've assigned the value 0 to it. We've got a bucket, we've put the name total on the bucket, and then we've put the value 0 inside. Further down the page, we have we've updated the value in total, so we have total equals bottles times bottle volume. Bottles and bottle volume are previously defined variables, and this expression on the right-hand side is going to replace the value in our variable total. So we're replacing the value inside that bucket. Okay, and then slightly further down the page at the very bottom, we've got total equals total plus cans times can volume. We have previously defined variable names, so cans and can volume, but we can also use the same name in both sides of our equal sign. Okay, and we'll see how this works in the next couple of slides. So what's the point of having variables? Why do we need them? Well, let's take quite a simple example. We're going down to the local corner shop and we want to buy some cans, or we want to buy some 2-litre bottles of Coke, let's say. Soft drinks are sold in cans and bottles. A store offers a 6-pack of 12-ounce cans for the same price as a 2-litre bottle. Which should we buy? So we want to work out the answer of which is better value for money for us, a 6-pack of cans or a 2-litre bottle. And we're going to need some variables to work this out. So we're going to need to know the number of cans per pack. And the type of number this is a whole number. You can only have a whole number of cans in a pack. You cannot have 3.5 cans in a pack. You could only have 3 or 4. In our case, we've been told that there are 6 cans in a pack. We also need to remember how many ounces there are per can. This could be a fractional amount. You could have cans that store 6.5 ounces or 4.5 ounces or values like that. So this time, instead of it being a whole number, it's going to be a number with a fraction. We also then need to store the ounces per bottle. So we've got the ounces per can, and we're going to also need the ounces per bottle. And again, this value could be a fraction. We could have 12.5 ounces or 32.5 ounces in a bottle of pop. So why do we need different types of data? What are these different types of data and why are they needed? Well, we're going to kind of focus on 3 different types of data. In this chapter, we're going to focus on whole numbers. These are called integers. They have no fractional part. They're things like the number 7 or 32 or -65. We're also going to look at numbers with a fractional part. These are referred to as floats. They can be anything like 8.88, 7.93, or -12.4. And then we're also going to look at sequence of characters, which is referred to as a string. Strings can be things like the name Bob, and they appear within quotation marks. Okay, so the type of information currently stored by a variable is indicated by whatever is to the right of the equal sign. So cans per pack, in the example at the bottom, has the value 6. That's a whole number, so the cans per pack is an integer. That's its type, while cans per volume is storing a float of 12.0. So can volume is a float. That's its type. So why different types? Why are we using these different types? Well, if you think back to maybe our bucket analogy or maybe our multi-story car park analogy, different car parking spaces may be meant for different types of vehicles, right? You might have specific car parking spaces for bicycles and motorbikes. Maybe you have specific car parking spaces for full-size vehicles or electric vehicles. If you want to park a limo, you're going to need a very specific type of space. And this is kind of why we use these different types. Okay, so sometimes when you just type out a number, the compiler that's used to compile your code has to guess what type it is. So if your compiler sees something like the number 6, it's going to give it the type integer. An integer has no fractional part. If it sees something like -6, again, it's going to be an integer because integers can be negative. And if it sees a number like 0, it's also going to treat that like an integer because 0 is an integer. Now, things like 0.5, the compiler is going to treat as a float. This is a number with a fractional part, and that has the type float. Now, that still holds true if we look at a number like 1.0. Because of the 0.0, it has a fractional part and has the type float. And then if we store something in scientific notation, so 1e6, which kind of stands for 1 times 10 to the 6, that would be stored again as a float, even though its value is 1 million. So numbers in scientific notation, or exponential notation always have the type float. And you can also have negative exponents, so 2.96 e minus 2 stands for 2.96 times 10 to the minus 2, which is the same as 2.96 divided by 100, which is 0.0296. And that would also be given the type float. Now, Python doesn't like it if you try and write numbers and use comma separators. So if you were trying to write 100,000, don't put a comma in after three spaces, three place values, because it doesn't like using the comma as a separator. Also, Python's not going to be happy if you try and use fractions. So instead of writing something like 3.5, you need to write 3.5. So here are some naming conventions for how you should name your variables. Names should describe the purpose of the variable. Something like can volume is much better than CV, because can volume clearly indicates what the value is referring to. CV could mean lots and lots of different things. And then there are some simple rules. So variable names must start with a letter or an underscore. Continue then, as you name your variable, with letters, uppercase or lowercase, digits, or more underscores. You cannot use symbols in your variable names, so you can't use things like question marks or the percentage sign, and you also cannot use spaces. Okay, you cannot have spaces in your variable names. Typically, we try and use CamelCase notation, so the first letter in our variable name, like in can volume, is a lowercase letter, and then every new word we uppercase, so the V in volume is uppercase. Okay. And then finally, don't use reserved Python words. We will look at some reserved Python words in the future. Okay, so here's a nice table for legal and illegal variable names. Something like can volume 1 with a lowercase c and an uppercase v is a great variable name. Variable names can consist of letters, numbers, and the underscore character, and typically we're trying to follow CamelCase notation. We could use a variable name like x. If you come from a maths background like I do, that's quite common. It's legal in Python, you can do it, but it's not suggested. It makes your programs really hard to understand, especially if it's someone else coming in and trying to read it, because they don't really understand what the variable x is representing. It's much harder to tell that x is representing can volume than a variable name called can volume. In the third row, we have can volume with a capital C. Now, variable names in Python are case sensitive, so there is a difference between can volume with a capital C and can volume with a lowercase c. Okay. It also will violate our naming convention, and the naming convention we're using is CamelCase. We start with a lowercase letter and then capitalize every new word. Variable names cannot start with a number, so 6-pack, referring to our 6-pack of cans, would not be valid in Python. We cannot use spaces, so something like can space volume would not be allowed. It would cause an error in Python. Class is a reserved word in Python, so we cannot use that as a variable name. And we also cannot use symbols, such as a slash or a decimal point in our variable names. So litre per fluid ounce, written with symbols, would give us an error if we try to use that in our Python program. Okay, so now we get on to variables, kind of updating variables, and the first time we declare a variable. So if an existing variable is assigned a new value, that value replaces the previous contents of the variable. So for example, we have cans per pack equals 6, and then the next line of code is cans per pack equals 8. And the way this works is we kind of can look at the numbers. It's going to go 1, 2, then 3. So because this is the first assignment, the variable is created. We get a bucket, and we put the name cans per pack on the front. Now that we have our bucket, we can store some value inside it. The variable is going to be initialized by storing the value 6 inside that bucket. Okay, and then we get onto the next line of code, which says cans per pack equals 8. this is the second assignment, and it's just overwriting the value currently stored in cans per pack. So we did have the value 6 in our bucket called cans per pack. We're now going to empty that bucket and put in the value 8. Now, earlier on, I mentioned that you could have the variable name on both sides of the equals, and there is a specific way that Python deals with this. So let's take the example cans per pack equals cans per pack plus 2. Okay, so the first thing we do is we calculate the right-hand side of the assignment. We calculate this cans per pack plus 2. So we find the value inside the bucket cans per pack, and we add 2 to it. The current value in cans per pack is 8. 8 plus 2 is 10. So we know that the right-hand side of this assignment has the value 10, and then we're going to store that result in the variable named on the left-hand side. So we're going to store that new 10 value inside cans per pack. Okay, some extra programming tips all about constants. A constant is a variable whose value should not be changed after it's assigned an initial value. So something like bottle volume, once it's been assigned the value 2, or 2.0 here, so it's a float, is not going to change anywhere in our program. We're not going to change our bottle volume. It's good style to use named constants to explain numerical values, to be clear, to be used in calculations. So if you look at the 2 lines of code, total volume equals bottles times 2 versus total volume equals bottles times bottle volume, the second line of code is far clearer to what this magical value 2 actually means. That magical value 2 is actually standing for the volume of an individual bottle. Okay, so a programmer reading the first statement may not understand the significance of this times 2. Also, if the constant is going to be used in multiple places and needs to be changed, we only need to change the initialization. So let's say we used bottle volume in multiple places, and all of a sudden Coca-Cola came out with 1.5 litre bottles. I only have to change one instance of the variable, so bottle volume equals 1.5, rather than having to go through my code and changing every times 2 into a times 1.5. Okay. Naming convention with constants, we typically use all uppercase letters, which helps distinguish them from variables, and we use an underscore to separate the words. So bottle underscore volume, all in capital letters, equals 2, would be a constant. Max underscore size, all in capitals, would again be a constant, whereas something like tax rate with a lowercase t and an uppercase r for rate would indicate that it's a variable to us, and a variable kind of has a value stored inside it which might change. In our very first Python program, we started our program with a hash symbol. That indicates the start of a comment. People like using comments. It makes it easier for people to understand the code, humans to understand the code, not computers. So typically we advise that you use comments at the beginning of each program to clarify the details of the code, what the program is being used for. The comments are really, really useful for humans who read the code. The compiler is going to ignore comments. So the comments that you write will have no effect on the compiler. So as an example, we start our program with some comments, and the comments this time are, this program computes the volume in litres of a 6-pack of soda cans, and the total volume of a 6-pack and a 2-litre bottle. Okay, and then slightly further down, we've got another comment telling us that litres in a 12-ounce can and a 2-litre bottle. So it's giving us information of what these variables stand for, and then again on line 10, number of cans per pack, it's telling us what this variable is standing for. Okay, and then let's look at maybe some common errors that can occur when using variables. The first big one would be an undefined variable. And what happens when you have an undefined variable is you've tried to use a variable before you actually have defined what that variable is. So you have to define your variable before you use it. So if you look at the bottom lines here, we've got can volume equals 12 times litre per ounce, but we haven't actually defined what litre per ounce is yet. We do that on the next line down. This is going to cause an error. It might be worth pausing the video here and typing this out and seeing what type of error you get. Okay. The second kind of error that's quite common is rounding off errors. So computers store infinite precision values in finite precision. Floating point values basically are not exact. And this is a limitation of a finite amount of space, as well as storing things in binary. So something like price equals 4.5, quantity equals 100, total equals price times quantity. So we're going to do 4.35 times 100. That should be 435. But actually, the value computed by Python is 434.999999999, and so on. You can deal with round-off errors by rounding to the nearest integer, or by displaying a fixed number of digits after the decimal separator. And we'll look at that, I think, in a later session. Okay, and then we have more common errors, so unbalanced parentheses. Okay, these are sometimes called brackets. If we look at the expression here, we have open bracket, or open parentheses, a plus b, close parentheses, times t divided by 2 times 1 minus t. And what's wrong with it? Well, hopefully you can spot it, but kind of this parenthesis and this parenthesis are kind of paired together. This parenthesis and this parenthesis are paired together. But this parenthesis has no closing partner, and that would cause an error if we try to compute using Python. Now, if we look at this bottom example, we have a plus b times t, and then a close parenthesis divided by 2 times 1 minus t. This expression has 3 open parentheses and 3 close parentheses, 1 open, 2 open, 3 open, 1 close, 2 close, 3 close, but the expression still isn't valid, it's still not correct, because they're not balanced. These two pair up, and then I've tried to close a parenthesis before opening it. These two pair up, but I've opened a parenthesis, and I have never closed it later on in the code. Okay, again, you might want to pause the video and type these out onto Python just to kind of confirm this for yourself. Okay. Python, being a computer programming language, supports all the same basic maths that you would be used to using a calculator. So things like addition, subtraction, multiplication, and division. You do write your expressions slightly differently, though, on Python than how you would maybe on a piece of paper with a pen. So typically using algebra, you'd write something like a plus b all over 2. In Python, you'd have to write it as open parentheses, a plus b, close parentheses, divided by 2. Precedence, so the order of operations, is the same as it is in algebra. You might have been taught PEDMAS or PIDMAS or BEDMAS or BODMAS. So parentheses or brackets, then exponent or orders, then multiply and divide, and finally addition and subtraction. So this is the order in which operations should be performed. Now, Python's quite a nice programming language because you can mix integer and floating point values in your arithmetic expressions, which will result in a floating point value. So 7 plus 4.0 is an integer plus a floating point number. Python's going to deal with that actually quite nicely and return a floating point value of 11.0. Kind of a slightly more complex area are things like powers and roots. So you might have heard of squaring things and also square rooting things, but higher powers are also possible. So something like b times 1 plus r over 100 to the power of n becomes b times, so this part is the same, we're happy with that, open bracket, and then open another bracket for 1 plus r over 100, and then times n, close bracket. This double star stands for exponentiation. So a single star is used to multiply, double star is used for to the power of, right, raising something to the power. And here's kind of an explanation of how this line of code turns into this algebraic expression. So r over 100 is kind of r over 100, which we're happy with. 1 plus r over 100 looks like this. the external brackets, kind of put the brackets around it, and we raise that to the power of n. So that double star is raising something to the power of, or exponentiation. And then finally we multiply by b. Okay. So here are a bunch of arithmetic expressions. We have x plus y over 2, is how I would write it on a piece of paper. In Python, open parentheses, x plus y, close parentheses, divided by 2. Okay, the parentheses are required here because x plus y divided by 2 computes x plus y divided by 2. Right? It doesn't do the whole top divided by 2. It's not all over 2. It would just be y over 2. Xy, or x times y divided by 2, we can write as x times y divided by 2. Here, parentheses aren't required because the operators with the same precedence are evaluated left to right. And in PEDMAS, division and multiplication have the same precedence. 1 plus r over 100, all to the power of n. We have to use parentheses here to make sure it's the 1 plus r over 100. That whole thing is being raised to the power of n. If we missed out the brackets, we would have a different calculation. And maybe you want to see what happens if you miss out the brackets, or the parentheses. Root a squared plus b squared becomes square root, or sqrt. Open parentheses, a double star to the power of 2 plus b double star to the power of 2. To use the square root function, we have to import that from something called the math module, which we'll look at later on. And then something like pi, which is an irrational number, we can call by typing out pi. And again, pi is a constant declared in the math module, and we'll look at the math module later on. So then we move on to functions. A function is a collection of programming instructions that carry out a particular task. We have already used the print function. And what does the print function do? It displays information to the shell. But there are lots of other functions available in Python. Most functions return a value. That is, when the function completes its task, it passes a value back to the point where the function was called. The abs function, ABS, standing for absolute value, returns the absolute value stored inside its parentheses of the argument that we give it. So abs of minus 173 returns the value 173. The value returned by the function can be stored in a variable, so typically maybe something like distance equals abs of x, or absolute value of x, is going to return the absolute value of x and store that value inside the distance variable. There are some built-in mathematical functions that we can use, things like absolute value, which returns the absolute value of x. Round x will round the floating point number x to the nearest whole number, or round x comma n will round it to n decimal places. Max of x1, x2, ... xn is going to return the largest value, the maximum of the arguments supplied to it, and min x1, x2, comma ... xn is going to return the smallest value, the minimum value of the arguments being provided. There are more functions that we're going to kind of get used to using, so things like int and float. These are casting calls and convert between integer and floating point values. So let's say we had balance equals total plus tax, and balance is a floating point number. Then if we call the function int on balance, that's going to turn it into an integer type, and we can store that new value in the variable dollars. When you do a conversion from a floating point value to an integer type value, you're going to lose your fractional part of your floating point value. No rounding is occurring. It's just going to chop it off. We aren't typically going to need to convert floating point values to integers that often. It's more used in other cases. And now we can talk a little bit more about modules. So this is kind of going back to the math module that we talked about earlier. So a standard library is a library that is considered part of the language and must be included in Python's system. Python's standard library is organized into lots of different modules. And a module contains a bunch of related functions and data types that are all similar in some way. They all do a similar purpose or all work for a similar sort of idea. the functions defined in a module must be explicitly loaded into your program before they can be used. So if you want to use some of the fancier math functions, you're going to have to load in that function from the math module before you can use it. For example, if you wanted to use the square root function, which is quite a common function people will be using, we're going to have to import it from that math module. So from math, import square root, imports the square root function from the math module into our program, so we can call it just by typing in square root and then open bracket and providing some argument. Okay, so y equals square root of x. So here are a bunch more functions from the math module that you might want to be using. Things like square root, so square root of x, where x is a number greater than or equal to 0. Trunc, which truncates a floating point number into an integer. Cos, which computes the cosine of x, where x is given in radians. Sine of x, the sine of x. Tan, the tangent of x. Exp of x, or the exponentiation of x, so e to the x. Degrees will convert x in radians to degrees, and there's a mathematical calculation of how that works. And then similarly, radians converts degrees to radians. Okay. And then we have logarithms. So log of x is going to compute the natural logarithm, which is log to a base of e, or we can call log x comma base, and we can provide the base to whatever value we want it to be. Okay, so that's everything for this second chapter. There's been quite a lot of information here, so feel free to pause the video, go back and rewind it, and check specific sections to ensure that you have a good understanding of these data types and variables. Okay, and again, variables, I like to think of them as buckets with labels on and values stored inside them. I will see you shortly for the third session.